This topic on limits is about finding limits analytically, meaning using algebra. We just learned how to use numerical approaches where you plug in numbers very close to the value of x, and a graphical approach where we look at the graph and see what the graph is approaching for both sides of x. Those methods are both effective, but sometimes they don't give us the exact answer. So today's lesson, or this lesson, is going to be using algebra, so we definitely get an exact answer to find our limits. First, we need some properties of limits. So, given, if you know, the limit of some function a of x, as x approaches c, is some number a, and the limit of some function b of x, as x approaches the same number c, is some number b, then we have this list of properties here. So basically you have a function a of x, a function b of x, the limit of this function is a, the limit of this function is b, both approaching the same number. You have 5 properties here. The first property is a scalar multiple. So if I take this function a of x, and I multiply it, that's a times sign. If I multiply it by n, the limit as x approaches c of n times the function is going to be n times that original limit. So if you multiply the function by a number, the limit is going to be multiplied by that same function, or that same number. We have the sum and difference property. If you take these two functions, a of x and b of x, and add or subtract them, the limit as x approaches c for that sum or difference is going to be the sum or difference of the limits added up. So if you add or subtract the two functions, the limit's going to be the addition or subtraction of the two limits. Product rule. If you multiply the two functions, your limit's going to be the product of the two answers, of the two limits. Quotient rule, again, very similar, straightforward. A of x over b of x, the limit's going to be a over b, with the distinction that b cannot be 0, otherwise it would be undefined. And finally, the power rule. If you take the function and raise it to a power, the limit can also be raised to the power to give you a new limit, or a limit for the new function. First thing you want to do when looking to find a limit is to try direct substitution. Meaning, if you want the limit of a function as x approaches c, as x approaches some number c, the first thing you want to try is taking that value c and plugging it into the function. See if it gives you a number. There are all kinds of functions. We have a constant function, y equals 7, f of x equals -2, where you would have a horizontal line as your graph. You have a power function, x to the n, x cubed, 5x to the 10th, something like that. A polynomial function, a combination of some powers, 3x squared minus 4x plus 7. Rational function, where you have a numerator and denominator. A radical function, where you have a root, square root of a function, cube root of a function, 10th root of a function. A composite function, where you have a function within a function. For instance, the square root of 5x to the 5th, something like that. Or a trig function, sine, cosine, tangent, secant, cosecant, cotangent. All these types of functions, first thing you want to try, use direct substitution. Plug in c into the function to see if you get a value. If you get a value, that value is your limit. If not, if it's undefined, you get 0 over 0 or some number over 0, you get 0 in the denominator, then you're going to have to try another approach. You can go to numerical or graphical approach if possible, but right now we're going to focus on an analytical approach. First paragraph sums up when we want to use some algebra to solve it. When you use direct substitution, if you get a non-zero value in the numerator and 0 in the denominator, meaning some number on the top, 0 on the bottom, then your limit does not exist. 0 in the denominator makes the function undefined, or makes the fraction undefined, therefore your limit does not exist if there's a non-zero number in the top. If you get a 0 in both the numerator and the denominator, you plug in a number in a rational function, and you get 0 in the top, 0 in the bottom, that is called an indeterminate form. That means you cannot determine the limit from that form of the expression or the function, and you're going to have to try another approach. So we're going to look at factoring to find a limit. We get our function, our limit, as x approaches 3 of x squared plus 2x minus 15 over x minus 3. So there's our original question, find that limit. Always try direct substitution first. Take 3 squared is 9, 2 times 3 is 6, that comes up to 15, minus 15 is a 0 in the numerator. Three minus 3, 0 in the denominator, there's the indeterminate form. This means we have to try to get this expression in a different form. Often you're going to look to factor. We look at the trinomial up top, relatively simple to factor, so we're going to rewrite this. The limit as x approaches 3 of x plus 5 times x minus 3 all over x minus 3. Often when you have a limit problem like this, the denominator will be a factor of the numerator. So it might help you figure out how to factor that top. Take a look at this. Cancellation of your x minus 3 term. So this is an equivalent form. So now we have the limit as x approaches 3 of x plus 5. Now that we've simplified it, use some algebra to break it down. Now we try direct substitution. As x approaches 3 plus 5, so this limit equals 8. This is an example of two functions that agree with each other at all but one point, meaning their graphs are identical except at one point. The graph of x squared plus 2x minus 15 over x minus 3 is the same as the graph of y equals x plus 5. Same exact graph, except where x equals 3, because that makes this undefined. So you would have a hole in your graph there. But this function, even though it's rational with a quadratic term on top, actually looks like a linear function. Here's a picture of it. Y equals x plus 5 is this graph here. But we have to exclude the value at x equals 3, so we have an open circle. As you can see, using a graphical approach here, if you trace this function from both sides, the limit as x is getting close to 3 is in fact 8. Two functions that agree at all but one point. So a rule you want to think about, if you get the indeterminate form of a function, look to simplify. Oftentimes, factoring is the way to go, the simplest way that will give you an exact answer. Now we have our next function, our next limit problem here. Limit as x approaches 0 of radical 5 minus radical x plus 5 over x. So we plug in 0, radical 5 minus radical 5 is 0 over 0. Again, indeterminate form. Always try direct substitution. Plug that in, we get 0 over 0. We have to do something here. Excuse me. Well, there's no factoring. So we have to do another approach here, still another algebraic approach. We want to change the form of this by multiplying the whole thing by some form of the number 1, by some fraction where the numerator and the denominator are the same. We just have to select the form of 1 that we want to use. We're going to go back here, back to algebra 1, a squared minus b squared, the difference of squares, factors into a plus b times a minus b. So if you have an a plus b and an a minus b, multiply them together, you get the first term squared, the second term squared, the middle terms wipe out. That helps us here because we have two terms, both with radicals, so we want to square them both to wipe them out. So we're going to use this idea, a plus b times a minus b. Here you have square root of 5 minus square root of x plus 5. So we're going to multiply this by the square root of 5. Instead of minus, we're going to add the square root of x plus 5. Now I want to multiply this by 1, so the numerator and denominator have to be identical. It's this one. So I multiply the numerator and denominator by the same thing, using difference of squares to pick what I'm going to get. A squared ends up being 5, square root of 5 squared squared, minus b squared, which is x plus 5. When doing this, make sure you realize that x plus 5, that whole term is being subtracted, so you throw your parentheses there. All over the denominator x times square root of 5 plus square root of x plus 5. So we're looking for the limit as x approaches 0. 5 minus x minus 5. 5's cancel, so you're left with a negative x on the top over x square root of 5 plus square root of x. By multiplying this original expression by a form of the number 1, I have now manipulated it into another form where x's will cancel. That x cancels with that x, leaving a negative 1 as my numerator. Now you can use direct substitution. Plugging 0 in for x, you get negative 1 over square root of 5 plus square root of 5, which gives you negative 1 over 2 square roots of 5. If you wanted to, you could clear this square root of 5 out of the denominator. In this case, it doesn't really matter that much. The idea here is this would be a very difficult problem to find the limit of using a numerical or graphical approach. This is an irrational number, so no matter how close we get, it's going to be hard to get an exact numerical value plugging in numbers closer and closer to 0. Same graphically. It will converge on a number, but it's going to be very hard to tell what that number is just by looking at a graph, since it's not going to fall perfectly on one of the scales. Now we have two special trigonometric limits. Limit as x approaches 0 for both of these. Sine of x over x, 1 minus cosine of x over x. Plugging in 0, you get sine of 0 is 0 over 0, indeterminate form. Plugging in 0 for x, cosine of 0 is 1, 1 minus 1 is 0, over 0. So these values, this 1 and this 0, are special values that are found using something called the squeeze theorem that's more appropriate to go over in a classroom setting with your teacher. So for now, we're just going to talk about these are the values of these two limits, and we're going to see where they occur. These are just two limits that you're going to have to memorize. These are special limits that come up once in a while in limit problems. So you get this limit question here. 3 times the tangent of x times the secant of x divided by x. Like we said, always use direct substitution first. 3 times the tan of x, tan of 0 is 0. Sec of 0 is 1. 3 times 0 times 1 is 0. Over 0, indeterminate form, so we have to do something with this. What I would suggest is to rewrite the tangent and the secant with a numerator and denominator. So rewrite this as 3 and x. This 3 stays in the numerator, this x stays in the denominator. Now take your tangent of x and break it up. Tangent of x is the same as sine of x over cosine of x. Take your secant and break it up. Secant is 1 over cosine of x. Now, we can separate this because of those properties and limits we saw in the beginning. You can take two limits and multiply them together or you can take two functions and multiply them together, and take their limits and multiply them together. So what I'm going to do is I'm going to break this up. Looking back, if I have something in the form of sine of x over x as x approaches 0, I know what that limit is, so I want to try to find that. Have a sine of x, have an x. So I'll rewrite this as the limit as x approaches 0 of sine of x over x times the limit as x approaches 0. Sine of x and the x are gone. I'm left with a 3 on top and a cosine squared of x in the denominator. Going back to our special trig limit, this limit here is 1 times the limit as x approaches 0 of 3 over cosine squared of x. Plug in 0 for x. Cosine of 0 is 1. 1 squared is 1. 3 over 1 is 3. So this limit here, whole thing, equals 3. Last example. Limit as x approaches 0, sine of 10x over x. So this is already very close to the sine of x over x form. We want the angle to be the same as the denominator. I cannot factor a 10 out of an angle. Sine of an angle, that angle has to stay the same. 10x is the angle. So I'm going to take this expression and make the bottom, the denominator, the same as the angle. In order to do that, I'm going to take the expression and multiply it by 1, and I have to pick a specific form of 1. In this case, I want to multiply it by 10 over 10. So this now becomes the limit as x approaches 0 of 10 sine of 10x over 10x. This limit here has a value of 1. The limit of a constant is the constant itself, so it's going to be 10 times 1, and that limit will be 10. I want the angle and the denominator to be the same if we want to use that special trig limit.